so for this question and answer. Oh, yeah.
See a reply from me.
Yeah.
So I did not.
Phase closure. Yeah, right. That's true. Hi. We're just looking at the sequence.
Yeah.
But did these guys also have it?
I don't know. I didn't.
So.
Well, I think we can start with these.
Yeah, but should we project them? Then they...
USB or something.
Yeah.
USB. Oh, they could, I mean,
I've got a USB stick.
We can read it up.
Just give them the general topics and ask for.
Yeah.
I mean, we can read these if you want word for word. Or we can
Yeah.
say the general. Maybe.
Well, you know, but Paul, what is
It's kind of a pain for them to copy things around. I find. So.
But I think it's even more, let's say, dynamic if we would come just forward during that part and you know address it.
Listen to the session? Yeah. Yeah, I can call. Oh, well, maybe I'll just come up here and we'll just say,
Yeah.
you chaired yesterday's session, so that'll be fun to start up. If he's done, he's welcome.
Well, okay. Yeah. I think what we should try to do is to see if there's input from. So first, let's give a little bit of time until it starts to hurt, and then. I agree. It shouldn't have come from us. Yeah. Otherwise, it's kind of. It's really that. Hi.
This is, as long as this is formatted properly, so I can read it on a Mac.
Read on Linux.
Let's see. All right. So where is the? Okay.
So it's the first speaker that you. What is it?
Give it a minute or two because it's the first one on the fourth.
Yeah, I think that's that's good.
This is a file that says fringe sequence. It'll be obvious.
So we're going to wait a couple of minutes just for people to drop in, and then we'll start. Let's give it a go. start?
Yep.
Okay, welcome everybody who got up early on the fourth day of the conference. It's a long week, but all the papers are about InSAR, and so it keeps us going. So let's begin this session, which is part 2 of Advances of InSAR Theory. And our first paper is entitled A Novel Multitemporal D-InSAR Phase Unwrapping Algorithm Based on Compressive Sensing and Minimum Cost Flow Techniques. The first author was, or is, Mohammed Yasser. He's not here, so Michele is going to give the talk.
So, good morning. Thank you, Howard, for the introduction. And thank you for coming so early for the first talk. So, I'm going to talk about a new multitemporal phase unwrapping algorithm for multitemporal DINSAR approach for the generation of the deformation time series. And this approach, this algorithm, has been developed by benefiting from the minimum cost flow technique and the compressive sensing theory. Even if the algorithm has not been developed for any specific multitemporal approach, we tailor the algorithm on the small baseline subset algorithm. I'm pretty sure that you know the SBAS approach, so I don't need to go in the details of the technique, because we know that SBAS has been presented more or less 20 years ago, has been applied with different SAR systems in different deformation scenarios for different applications. Here we have just a recent example that we produce by processing the Sentinel-1 archive collected over Europe between 2015 and 2019. So SBAS approach in the last 20 years has been validated and tested with, by exploiting different independent measurements such as GPS or inclinometers or leveling measurements. However, we know that the phase unwrapping procedure still remains one of the most critical procedure in the approach, and by improving the phase unwrapping, we can produce more robust deformation time series. So we work on the phase unwrapping procedure, and we start from the extended minimum cost flow algorithm that is the most largely used phase unwrapping algorithm within SBAS. The idea of the EMCF approach is to implement a cascade of 2 different phase unwrapping procedures, the temporal phase unwrapping and the spatial phase unwrapping. Both procedures are implemented by using the minimum cost flow approach. In order to carry out the temporal and spatial phase unwrapping, we have to build 2 different networks. The first one is relevant to the temporal domain. It's implemented in temporal and spatial baseline plane. Here on the left graph in the slide. And here each point represents a SAR acquisition, and each arc represents an interferometric pair. On the right, we have the spatial domain in the azimuth range plane. Here, each point represents a SAR pixel, and each arc is a phase gradient. So the phase difference between 2 pixels. In order to select the pixel to be unwrapped, we apply the triangular coherence. In other words, we estimate the coherence by taking into account the residuals within the triangles of the temporal domain network. And we select only the pixel that have coherence larger than a pixel threshold. Since we are using only very coherent pixel, we can assume that we don't have any effect related to bias or similar effect or similar behavior. In this work, we mainly work on the temporal phase unwrapping in order to improve the quality of the temporal phase unwrapping that constrain the spatial domain. To understand what we have done, let's start from a very easy example. It's relevant to tree acquisition, ABC. From these tree acquisition, we can generate three interferograms. And we know that if we are working with unwrapped data or correctly unwrapped data, we don't have any residual within the triangle. Of course, we can translate this simple equation in a matrix formulation. Here we have the whole network in the temporal domain. C represents the matrix of the temporal network, and Q is the number of triangles, M is the number of interferograms. What I have said is correct, is true in if we are working with unwrapped data. But if work with wrapped data, this one is not true. In particular, our condition is not equal to 0. But we can include the K vector in order to include the vector, the integer vector, corresponding to the 2 pi multiples that we need to add to the wrapped phase to unwrapped phase. In particular, we have the last equation that I highlighted in red. The problem is undersampled because the number of equations corresponding to the number of triangles is smaller than the number of unknowns. So we have an infinite number of solutions. But we can assume to search for the solution that corresponds to the minimum number of 2 pi corrections. This, in other words, corresponds to solve an L0 norm optimization problem. But unfortunately, this problem has no mathematical representation or computationally efficient solution. But we can benefit from the compressive sensing theory to convert the L0 norm problem in a L1 problem. We can do it when our solution, our vector is a sparse vector, when the K vector is a sparse vector. Sparse means, or a vector is sparse when the number of non-zero elements is much smaller than the number of elements of the vector. So if the number of 2 pi correction is much smaller of the number of interferograms. If this hypothesis is satisfied, we can convert the zero norm optimization problem in a L1 optimization problem. We can solve the L1 problems because we have several algorithms to solve L1 problems that are also computationally efficient. In our case, we use the iterative reweighted least square approach. So now let's try to understand how we benefited from this technique to improve the extended minimum cost flow algorithm. Here we have the spatial grid. The spatial grid, each arc is a phase gradient between 2 pixels. So let's consider just one arc. We have the phase corresponding to this arc in each interferogram. So we have the phase of each arc in each interferogram. The idea is to solve to unwrap each arc in the temporal domain in order to constrain the subsequent spatial phase unwrapping. In other words, we can use the unwrapped phase in the temporal domain in order to constrain the spatial phase unwrapping, in order to have an input, a starting point for the spatial phase unwrapping. Moreover, from the temporal domain, we can retrieve also a cost function. In particular, in our case, we use an on-off cost function. We assign 1 to the arcs where we are not confident on the quality of the solution. And we assign a very large cost, 100,000, to the arcs where we are confident on the solution. to understand or to decide if the solution is good or not, we use two different check functions. In particular, we use the temporal coherence that here I call gamma R&D, and the number of corrections that represent the sparsity of the vector. For the arcs where one of these two check is not satisfied, the arc is not, we consider the arc not well unwrapped, and we assign the one value. In the other case, where both thresholds are satisfied, we assign the large cost. In this way, we can retrieve a cost function for the spatial phase unwrapping. Of course, we can change the two thresholds in order to retrieve different cost functions. In particular, by changing TH and TH sparse, we can retrieve a different cost function. With different cost function, we can implement a different spatial phase unwrapping. In other words, we can iterate the spatial phase unwrapping in order to have more solution in the spatial domain that we can average, properly average, to retrieve the final solution. Here, in this slide, I represent how we can average the different solutions. So by changing TH sparse, we retrieve a different cost function. For each cost function, we have different spatial phase unwrapping. So we have phi1, phi2, phi-n. For each solution, we apply SVD or least square. We retrieve time series, and we can extract, we can compute the phase residuals. Phase residuals represent the error of our system. So from the phase residual, we can retrieve the weights, and the weights with the equation. No, sorry. This equation. That, and the weights can be used for a weighted average of the solution to retrieve the final, more robust result. So now let's move to see some results that we retrieve by processing Sentinel-1 data. In particular, the first data set is relevant to the Monte Etna, that is the largest volcano active volcano in Europe. We process the ULA Sentinel-1 archive collected between 2015 and 2019 from descending orbits. Here we have the results that we achieved from the EMCF and the CS-based phase unwrapping procedure. I'm showing you the mean deformation velocity maps. It's not easy to appreciate the improvement that we achieve by applying the new algorithm, because the EMCF is a well-established algorithm that demonstrated the capability to unwrap multi-temporal InSAR data. However, if we zoom on the top of the Etna, where we detect the largest deformation, we can see important differences between EMCF and CS-based. In particular, we are considering points with a large coherence, larger than 0.9. With the EMCF, we unwrap more or less 93% of the points that we compute with the triangular coherence. And here we have the results of the CS-based. You can appreciate how, with the new algorithm, we are able to go on the top of the Etna, where the largest deformation has been detected. Of course, we can have a look to the time series to understand how the new algorithm is able to unwrap the data. Here we have points relevant to the western flank of the volcano. I wanted to highlight that Etna is an active volcano that is where several eruptions occur in this period. But here the most important. okay, are relevant to the 2017 and the 2019 eruptions that generate a sequence of seismic events. In the last plot, we have the difference between the two solutions. We can appreciate how the new procedure is able to detect around 3-4 centimeter jump of 3-4 centimeter in corresponding of the 2018 and 2019 volcanic activities. I want also to highlight that we improve the coherence from 0.8 for the EMCF and 0.9 for the CS base solution. Here we have another point relevant to the eastern flank of the Etna. In this case, the main unwrapping errors are relevant to the 2017 eruption. In this case, we lost more or less 6 centimeters with the EMCF procedure, and the coherence also in this case increased from 0.8 to 0.9. Another point, in this case, we have several unwrapping errors, mainly in corresponding of the 2019 eruption, and also in this case, the coherence increased from 0.86 to 0.9. So we understood that the algorithm, the new algorithm, is able to preserve the capability of the EMCF approach to unwrap very large data, so to unwrap very large areas. However, the new approach is able also to better tackle very large nonlinear deformation signal, in particular when in corresponding of volcanic unrest or earthquakes or this kind of deformation that usually are very, very hard to be managed by phase unwrapping techniques. In order to stress the capability of the algorithm to work with nonlinear deformation signals, we process the Stromboli area. Stromboli is a very small volcanic island located in Mediterranean, and is interested by very strong deformation related to the activity, volcanic activity. Also in this case, we process the Sending Sentinel-1 data set acquired from 2016 to 2021. So let's go faster. Here we have the two results relevant to CS EMCF. Also in this case, we cannot appreciate in this figure the improvement, but if we zoom in the Sciara del Fuoco is a sliding area located in the northern flank of the volcano, we can see the improvement that we achieve with the new algorithm, in particular along the edge of the Sciara, in the middle of the Sciara. All the points, the more or less 200 points that we retrieve are located in this area. And if we have a look to the time series, we can see how the volcanic activity that occurred in 2019 generated a very strongly nonlinear pattern that is not detected by the EMCF, but is detected by the new approach. In particular, in this case, we correct more than 10 centimeters of deformation for a total deformation about 20 centimeters. More interesting, if we have a look in the middle of the Sciara, where the total deformation exceeds 40 centimeters. Also in this case, we correct a jump about 20 centimeters in corresponding of the 2019 activity. And this nonlinear behavior cannot be detected with the EMCF. So I have concluded, and thank you very much for your attention. That's all.
Thank you. We have time for one quick question. Do I see a question? Charlie.
What do you think is the influence of the phase closure discussions that we've had earlier on phase unwrapping?
Here, the phase closure is not a problem because we are considering only points that don't have residuals within the triangles. So we don't have residual because only very points with very high coherence, triangular coherence has been considered. So we don't have effect. No, multi-look. So in theory, there are pixels that are affected by bias or this behavior, but are not considered in the phase unwrapping because, sorry, I go fast. Okay, here. Only 0.9 or larger coherence points are considered.
Okay, thank you very much. We'll move on with the next talk. So this talk was about getting more pixels, and now we're going to get rid of pixels. But the fortunate thing is that these are decorrelated pixels. And this talk will be given by Howard Zepker.
Thanks, Ramon. Okay, so what I'd like to talk to you about today is essentially how we are trying to cope with the coming true onslaught of large amounts of data. So, here in Europe, there's going to be follow-ons to Sentinel-1, there's going to be Rose-L, there's going to be Harmony, there's going to, the whole list that we've seen. In the US, we have the InSAR mission launching next year. There's going to be a great deal of data coming, and at least in the US, we're thinking of going to future concepts where we might have whole constellations of satellites that are interrogating the Earth every 6 hours rather than every 12 days. So we really need to have a way to deal with these large amounts of data, and it is already impossible for any one of us to look at maybe you're doing a study that uses 5,000 interferograms. You can't go through and fix all the little things in each one. Especially if you're looking at lots and lots of baselines together to do SBAS calculations or whatever. I mean, the volumes are really, really large. And so we need to have a way to do this in an automated way where we don't have to interact very often at all with the system, and it spits out high enough level data products that these are useful for being applied in a number of different ways. One flip answer to this is, we're just going to dump it all into machine learning and it'll sort it all out. Well, I hope that that's where we get someday. We're not really quite ready for that. So what I tell people is that one of my future students is going to tackle that problem. In the meantime, we're going to try to do it in a more conventional way. So we're talking really here, even though the paper is a scientific result that is stated, what we're really talking about is the engineering problem for exactly how to do this. And so basically, how do we make InSAR time series that can be generated routinely and people don't have to interact with it, and that the results are robust and can go along in a reasonable trade-off of quality and speed. So the innovation here is less on the individual steps in doing this. We've seen a lot of good papers on these things, in fact, already in this year's FRINGE meeting. But we basically have put together these pieces that already exist into an overall data flow that includes developments from the last 25 years. And everything will work together in a nice, harmonious way to generate the data that we want. And hopefully, we will integrate this into packages such as the ICE package that's being developed at JPL. And we hope that it gets enough notice to make it into some of the other processing packages that many of us use. So the data flow at the very high level looks something like this. You can start with either L0 or L1 products. We actually prefer to start with L0 products in many cases for a variety of reasons, but there's no reason you can't start with level 1 data and go through the same thing. But essentially what we do is we generate geocoded versions of the single look complex images. Then we go through a PS filtering and interpolation step, which I'll get a little bit more detail into. And then it goes into the usual phase unwrapping and atmosphere removal and SBAS for the time series and then comes out with a result that is a time sequence of deformation across whatever the size of the scene is that we're doing. I'm not going to read all of these, but the details, as I said before, is that we start out with these level 0 products. We're using typically a PS filtering step, but you don't have to do that if you don't want to, but I'm going to show that it actually helps us in a couple of cases. We simply use snafu with, as it comes out of the box to do the phase unwrapping. You just heard other approaches to that even in the previous talk. You can stick in whatever that you want. For the atmosphere removal, there's been a number of discussions about that. There's lots of ways to use different models and so on and so forth, but we actually find that it works as well to simply do regression versus height of the unwrapped phases. And all these different algorithms, they all get rid of half the noise and half the noise stays. It may be a different half each time, but the overall result is always about the same. And then we know SBAS and everything is unweighted because that way we don't have to worry about a way to calculate the weights. So the way that we are doing our PS step, I'm going to spend a couple slides on that because not everybody may be familiar with the algorithm that we're using. It's fairly recent. But we start out by using an MLE criterion to pick the PS points, and we overselect on purpose. So here's a region in California's Central Valley. It doesn't really matter. That's why there's no labels on the image. But every white pixel is one that has been above a threshold for the maximum likelihood estimator. Again, the threshold is set low, and we know that we have many, many points here that are not true PS points. And so what we do then is that we send those to a cosine similarity measure, which goes through and makes sure that every one of the ones that we flagged was actually a PS. So as you can see, this has got a lot less white than it did before, but it still maintains quite a few of them. So we've gotten rid of all the false positives, and then we apply the cosine similarity again to all the unflagged points in here and fill in the remaining points that actually seem to be PSs. And we end up with an image that looks something like this. And given that this is an agricultural area, it actually fills in quite a bit. And then we take these individual points, and for everything that remains black in here, we interpolate given all the other points in the image. So we end up with continuous coverage. And if you do that, you get an image that looks something like this. It's the same area that we had before, and it's a subsidence bowl in the Central Valley. And in this particular case, the scale here is in terms of radians per day. And if you convert that to centimeters, you'll get what you get, but it matches reasonably well. We'll talk about that in a minute. And I also showed on here the location of GPS stations in this area, essentially to show that there are GPS stations in a lot of places, but they're not, as always, they're never exactly where you want them, and they're not particularly dense, and so we have the map from InSAR, which is much more dense spatially than what we had before. And if you take the ones that I saw there and that you saw labeled, we can look at a result of a derived time series here. So this is 5 years, or this is about 4 years worth of data. Shown here in green are the PS solutions. In red are the conventional SBAS only solutions, and then the dotted black lines are the GPS. They look like they're pretty comparable here, but we can make a little chart of what the RMS error is at every one of those GPS sites. And for the most part, the ones that have gone through this PS filtering have a fraction of the error than we got in the conventional SBAS. So this seems to be preserving some pretty good quality. Again, we remove the atmosphere simply through a elevation regression. I mean, I chose an example here from Hawaii because there's a lot of elevation change, and so it's a very easy plot. We just assume that it's linear, fit a line, subtract that everywhere, and that becomes the atmosphere-corrected image. Like I said, it gets rid of about half of the atmosphere. An example of that on the left are the raw interferograms over a variety of different periods. Once they go through then that atmospheric correction, you get what you have on the right, and it's much more clear where you do have the deformation along the volcanically active area in the lower part on the right-hand side of the image. But basically, it's blue everywhere else, so it's done quite a good job of removing the noise from the atmosphere. So let's look at two other examples. One is measurement of the creep rate along the San Andreas Fault in California, and the other is subsidence due to water withdrawal in an aquifer in Texas. And the goal for this one, it's an area that is pretty highly decorrelated because of the amount of vegetation in the area. And there's a poster over in the poster area describing more details of the water withdrawal problem that we had here. So here are the maps. San Andreas Fault is in California, for those of you who are less familiar with that. The specific example for the aquifer, it's in Texas. Texas is a big state, but it's a pretty big aquifer. So here's two different solutions. On the left is what we see in the conventional SBAS solution, and on the right is what we get from using the PS1. And we'll look at it in a little bit more detail in a moment, but it's much more clear, at least to me, because maybe I know what I'm trying to look for, that you really see the San Andreas Fault creeping section stand out quite well here. And it's hard to pick that out when you look at just the SBAS one. So the combined method is really doing quite a good job of isolating the real signal because we've thrown out all the pixels that add decorrelation. Here that is blown up a little bit again to show and highlight this creeping section that runs from a town called San Juan Bautista in the north down through another town called Parkfield in the south. Well, we can measure, if we assume that all the displacement that we measure is due to right lateral slip rates, which is a pretty good model for the large scale part of the San Andreas Fault, then we can get a fairly dense along track measurement of what the slip rate is in terms of centimeters per year. Now the average rate across the San Andreas Fault in this region in California over very long scales is closer to 2 to 3 centimeters per year. We're getting places where it has 5 centimeters, but that could be either that there are little bits and pieces that are moving episodically, or there could be some vertical motion and we've assumed everything is in the plane, and so that could be overestimating it. But the point here is that these points are actually pretty dense with latitude. And if you look here, there's a combination of, on the left, the white boxes show where we made those measurements. We just draw a little box around the fault and you average on one side of the box and the other side of the box and you plot that what was plotted in the point there. On the right are the GPS sites along this area. And there's not many parts of the world that are as instrumented as the San Andreas Fault. And you can see that our measurements are already much, much denser than is obtained from the GPS system. Just one slide on the aquifer region. The top is the SBAS solution. Something that you could convince yourself is a subsidence bowl, but in fact that's almost generated entirely by phase unwrapping errors in the SBAS solution. If you apply the PS filter and go through the data flow, you see something on the bottom, which I guess you'll have to take my word for it, but it's much more plausible given the watering records and such in this area. So in conclusion, I think that we have a pretty robust system. We basically give it a list, a latitude and longitude and say all the data from 2017 to 2021. It spits out the time series and they seem to match pretty well with what we know. You can run this standalone. You can integrate it within other processing packages. Probably all the pieces are in every one of the packages that you use. And so it's just a matter of writing the right Python script that runs things in order. But you don't have to fiddle with any parameters. It just goes. The performance is quite good in many cases. It's a finer spatial result, of course, than we get with GPS. The routine application, again, without any tuning, works quite well in highly decorrelated areas, which is what we tried to show with that image over the aquifer. It would be interesting, and I think in the future, to develop some context-sensitive parameter tuning. We don't do any of that now, but again, here's where places like some kind of artificial intelligence may be able to look at your data and say, well, you really want that threshold to be 0.85 instead of 0.8. Maybe that's a good thing. And so if you have a large enough data set, we may be able to learn enough to be able to feed these more automatic models that will, again, require less and less individual persons' interaction. So I will pause there, and I'm happy to take any questions.
Okay, thank you very much, Howard. Yeah, we have time for questions. Sang Ho here.
Thank you so much for your presentation. You lumped the atmosphere into regression, and that seems to solve everything. But we know that sometimes it's positively, sometimes negatively correlated with topography. And you showed us an example of Kilauea where it's mostly one side, so it's bounded by the mountain range. Could you elaborate a little more on the regression of what you did?
Well, the regression is just a regression. So basically, at some step, we have all the unwrapped interferograms. So for every unwrapped interferogram, we simply plot on the x-axis, the height, and on the y-axis, the unwrapped phase. We fit a line, and we subtract that everywhere. So we don't really think about it beyond that. So it's most obvious in a place like Hawaii, where you have the tall mountains, so there's a big elevation change. This was actually applied in that San Antonio data as well, which is flat. And so since there's no change in elevation, it doesn't even really matter what the phases are. It just doesn't try to apply a correction. So all it can correct for is the stratified component of the wet troposphere. And that's what gets corrected. And I made a pretty flip statement in that there's lots of different corrections, and they all get rid of half the noise, and they leave half the noise. And that's kind of what our experience is here. If you have a better algorithm, as I say, this is modular. You can pull out what we're doing, which is simple, and put in what you want, as long as you don't have to interact with it. So that is really the key in that, again, if you are generating 7,000 interferograms, you're not going to go in and solve each one of those independently.
Other questions?
Yes, first a comment to what, First, a comment to what Sang Ho was saying regarding regression with topography. I've seen in certain volcanoes where you will lose in a time series, half your true amplitude if you do that. So it must be used, I think, with caution. But my question is, or concern was, like in the Central Valley, if you're filling in big holes with this cosine interpolation, I guess I have two things that concern me. One is, what information are you truly getting in these big holes? Because the deformation there can be somewhat heterogeneous, even if in broad scale you get these large subsidence bowls. And so it just seems that you're kind of trying to add information where you really don't have it. And either you need a better sensor that can fill in, or just ignore it, because that's one case, but you may have other cases where you either have no idea what the functionality of the signal might be, or there might be more complex signals, and then you're kind of inventing something. So
yeah, okay, so that's a good point. Let's do the second half of what you said, because we addressed Sang Ho's already, but I take the note of caution. It is true that the only place where we have reliable measurements are at the PS points. Now, we happen to have a lot of PS points, but those are the only places where we know the data. The system does spit out that mask, so you can look at that. And so when you have a hole in between, it is simply interpolated from what we do. We pick between 20 and 50 nearby PS points, and then we fit some kind of a weighted average to that based on the distance. So if you have deformation between those big points, that are not adequately sampled with a PS point, yes, you won't see it. So you're stuck making a best guess. So you could just multiply the output data by the PS mask and say, here's where I believe the data, and we'll just ignore the rest of it. But we all have many, many analysis routines for working on spatially continuous data. And you just plug this into those same codes that you have, and whatever you're doing for your analysis will run. That doesn't mean it's going to be right, but it's going to run and probably not crash. So you're correct. We're not generating any kind of information that isn't already there. Now, what you can do, if you want to fiddle with it, you can lower the PS threshold a little bit, and it'll find a few more points. Those will be there. They'll be not as rock solid as the ones that we're using, but maybe that's a reasonable trade-off as well. Again, our goal was to do something that works most of the time and produces reasonable results. It's never going to be the best result that you could get from going in and hand-tuning all of your stuff. I mean, I guess, so it's a question of what we're trying to accomplish, I think.
Yeah. Thank you very much, Howard. I think we need to move on. So the next presentation will be given by Carlos Lopez Martinez. And it's called Reinterpretation of Temporal InSAR Coherence for Multitemporal SAR and Polarimetric SAR Data Classification.
Thank you, Ramon, for the introduction. Okay, so we're going to switch a bit topic here. So I'm going to present a little piece of work on how to reinterpret temporal coherence, and we will use classification here just as a tool to show the changes or what we observe in this case of reinterpretation. So this is the outline of the talk. So I invite those of you interested into the technical details that I will skip on the presentation to go to this paper we presented last year, where you have all the details. So basically, which is the context of this presentation? So when facing the analysis of temporal series, we ask ourselves, what is the temporal information, or where are the changes, or where we could identify changes? So we can identify changes on the temporal series of intensities, or in case of polarimetry, in the temporal series of covariance or coherency matrix. But in repeat SAR interferometry, we have also temporal information in coherence. Of course, this coherence depends on the targets, but has the little problem that we cannot use it when the coherence is very low. We have many scenarios where this happens: low temporal coherence, long temporal baselines, strong weather effects. So the goal here is to try to extract information from low coherence, but from our point, or philosophically, we wanted to try to find a mathematical network that may connect both sources of information to detect changes. So the theory is pretty simple. Here you have the classical expression of coherence. So it's very easy to decompose this coherence into two terms we call a symmetric term, which is in essence the classical coherence under the assumption of no radiometric changes. So there are no, in the case of interferometry or single-dimensional data, there are no changes in the intensity. So this is basically, this plays the role of the classical coherence. You can find the different multiplicative terms that affect that symmetric term. And we have a second term, what we call asymmetric term, which basically accounts for the departure of this symmetric assumption. Basically, this asymmetric term is the ratio between the arithmetic mean and the geometric mean of SAR images, and it's very nice and very simple to demonstrate that this term contains the same information as the ratio of intensities that many of us, we use it to detect changes in temporal series. Here you have the expression that relates both of the things, and the most important thing is that the range of value of the asymmetric terms goes between 1 and infinity. So if we take the inverse as a side product, we can have a bounded term that can be used to detect changes between 0 and 1. So we are not we don't have to face with infinities in detecting changes. We have a term very simple to detect changes between 0 and 1. So we are facing some scenarios. When there are no coherent changes, there are no radiometric changes, coherence is equal to 1. So life is easy. When we have only coherence changes, we turn out to be in the classical coherence. But when we have both coherent changes and radiometric changes, we have two situations. Case number 3 is what we call high coherence scenarios. So this is the most general case. You have radiometric changes, coherent changes, you cannot differentiate them. But when we are in low coherence scenarios, the symmetric term that basically goes to the classical coherence goes to 0. This will cancel the old equation of coherence, but we can observe that we can still get information from the asymmetric term, which basically contains the information departing from the symmetric assumption. So basically, this very simple piece of theory allows us to connect the changes that we can detect from coherence and the terms we can, or the changes we can detect from changes in radiometry. So at the end, we are able to combine the two sources of changes under the same mathematical framework. And as I said before, we have this asymmetric term that can be used to extract information of changes for low or even very low coherence scenarios. What happens if we add polarimetry? The advantage of polarimetry is it doesn't, when we apply polarimetry, we can extend the idea when we can still separate coherence, the Pol-InSAR coherence into two terms, but the advantage of polarimetry is that we can optimize. In this particular case, the symmetric assumption refers to polarimetric scattering mechanisms, not only to intensity. So if we apply optimization, the optimization of the symmetric term is the classical Pol-InSAR optimization, but we can also optimize the asymmetric term. And again, it is possible to demonstrate that this asymmetric term is related, in this case, with the polarization optimization ratio, which is used to, with polarimetry, to increase the separability of targets, if you want. Again, it's very easy to demonstrate that both are related, but in this case, as we have polarimetry, we have 3 optimum terms. We have 3 asymmetric terms due to the polarimetric diversity. Again, we have also shown, or in polarimetry, or when we talk with, when we work with multidimensional data, we have also the concept of distances between matrices. I mean, you have the geometric distance, the symmetric revision, which are dissimilarity, the likelihood ratio that are able to, that used to distinguish targets. So basically, this theory allows to decompose this distance measure into 3 components. So at the moment, we don't really know the consequences of this decomposition in terms of the distances, because still we haven't worked on that piece of work. Okay, we wanted just to show that somehow this decomposition of the coherence can be also related with the concept of distance, and we can separate it. We can decompose it at the end. So in order to show the information content of these terms, we will use classification. But bear in mind that here, we don't really care about classification. For us, classification is just a tool to show the information content. So we are using 3 data sets. First, a UAV SAR data set at L1, a temporal series of 5 images that refer to a high temporal coherence scenario, a low temporal coherence scenario in which we have 8 pulsar images with RADARSAT-2 in the Netherlands, in Flevoland, and finally, we also apply that to Sentinel-1 data. In this case, we have 32 images, dual pole over Barcelona, in Spain. And in this case, it's a mixed coherence scenario. So here are the data, 2 data of the data set, together with the ground truth for classification, so we can compare against a ground truth. So here is how the things look like. So on the top, you have the classical coherence. On the middle, you have these asymmetric terms. And on the bottom, you have the optimized value. On the right, what you have is all these values considered into the complete temporal series. So on the rows on the top, on the three row tops, you have the classical polarimetric coherence, and on the bottom, you have the optimized values. So as you can see, the three rows on the top and three rows on the bottom, they have different information, but we cannot really distinguish, or we cannot say that one is much better to the other to detect changes, because in this case, we are in a high coherence scenario. Nevertheless, if we go to a low coherence scenario, in this case is the Netherlands test site, the RADARSAT-2. If you go to the right and you look at the coherencies on the three rows on the top, and you look at the ranges of coherence, you see that you cannot distinguish anything because the values are very low. Nevertheless, if we go to the optimized asymmetric terms, you see that in that case you can see a lot of difference. So in this case, if you take a look to the coherences, they are very low. So you cannot obtain anything. Nevertheless, if you go to the case of these asymmetric terms or to the optimized values, automatically you get a lot of information in a low coherence scenario. For the Sentinel-1 case, in here the information is arranged differently on the columns, in the two first columns in each case for different classes, okay? You have the coherencies. Coherencies are in some cases low, in some cases high, but if we move to these asymmetric terms and the optimized asymmetric terms, you see that you can be much more sensitive to changes between the images. So how do we use this to demonstrate the information content? Again, we use classification. In this particular case, we use a recurrent neural network, recurrent in order to take into account, it's a convolutional neural network that it's recurrent in time, so we can take both into account space and time. So here are the classification results. The picture shows the classification results considering only coherences on the left. So you see that the overall classification accuracy is about 60%. Remember, this is a high coherence. But if we use the optimized coherence values, we increase the overall accuracy to 80%. On the right, you see the confusion matrices, and you see that with the optimized values of the asymmetric term, the confusion matrix is just much more clear. Just for reference, I present here which are the classification results using the intensities, and on the right T3, all the information we have, okay? So it's just as a reference. Of course, with the coherencies, we don't have access to the intensity, so we cannot achieve those numbers. But at least in a high coherence scenario, we can see that these asymmetric terms includes more information. What happens if we go to a low coherence scenario? The change is higher. In this case, if we use the coherencies, remember again, this is a low coherence scenario, you obtain an overall classification accuracy of about 35%. If we move to the optimized, we increase up to 85%. So the change is dramatic in this case, and it is shown, it's clearly shown in the confusion matrix. So as you can see, in low coherence scenario, this new asymmetric term is able to better differentiate the classes. But remember, the pictures are only classified results with the coherencies and the optimized asymmetric terms. Again, for comparison, we present the results with the intensity and with the full polarimetric information in this case, and in those cases, the classification is about 88%. So as you can see, this new term, I mean, of course, it doesn't beat the classification accuracy with the full information, but it's not really far. It's just about 4 or 5% far from those numbers. We go now to Sentinel. In here, and there is, we have also dual polarimetric, polarization, and the important message here is that in this case, despite we don't have fully polarimetric information, we can still optimize with dual pole, because in this case, the polarization is just a mathematical treatment, and we don't care about the scattering mechanisms. So in this case, we are still studying what happens with dual pole with Sentinel, but still in this case, we see that these asymmetric terms improve the classification accuracy. So also in this case, bear in mind that it's a mixed scenario, it's a low coherence, high coherence, so we have still to study the implications of this coherence. But still, in Sentinel-1, we can improve the extraction of temporal information. So just to close, we have presented here a new interpretation of the temporal coherence. So we have two terms, a symmetric term that basically takes into account the coherent changes under the symmetric assumption that no radiometric changes. We have a second asymmetric term, which basically accounts for the departure of this symmetric assumption. We have seen that this asymmetric term is especially useful when we face low coherence scenarios. So in our group, we are still not aware of the implication of the asymmetric term. We just use classification to see the information content. So there are many other applications where we could apply this technique. Okay? The usefulness of this term, we have proved it quantitatively. In terms of classification, we have seen that in some scenarios, low coherence scenarios, we can improve classification by 50%. In high coherence scenario, the improvement is not that high, but still we have been able to demonstrate that you can obtain improvements of about 20%. So this is the end of my talk, and now I'm open for questions. Thank you very much.
Thank you, Carlos. So we have time for a couple questions. I know, on Thursday, it's hard to think of new questions.
Thank you, Carlos, for a very good presentation. So I have two questions.
Speak up a little bit, didn't you?
Okay, a little bit. Okay. So I have two questions. So the first question is you told us that you're using the temporal coherence with polarimetric information. You can decompose into components, symmetries, and asymmetries. So the first question is it possible to get the same result if we combine in a certain kind of covariant matrix with a bit?
Could you repeat?
So we combine two components with temporals and polarimetrics to put it into the big covariant matrix and then decompose it in a certain kind of Kronecker products and get the first component and the second components. Can we get that similar performance or no? That is the first question.
I don't know. I cannot really answer that part because we have just established the mathematical framework and we are now going into the implications of that. So there are many, even me, I have a lot of open questions still to answer. So.
Okay, thank you. That's the first question. The second question is about the closure phase. So you studied about the temporal coherence. So basically, we have the time series data. So did you try to use in the phase closure to predict something? If there any expected to improve the performance for classification, if we include the phase closure in your procedure? No.
No.
Is there any expectation to improve or not?
No, I don't have that answer.
Okay, thank you.
Time for one more? I have a real quick one. It's a nitpick, but the asymmetric correlation, I notice, is defined such that its inverse goes from 0 to 1, but correlations always go from 0 to 1. So is there any reason that you didn't define it as 1 over your quantity, and then you'd have two correlations that both went from 0 to 1?
Sorry, repeat again.
The asymmetric correlation that we're talking about.
Yeah.
The range is essentially from 0 to infinity.
Yeah.
If you took 1 over that, then you'd have a correlation that goes from 0 to 1, which is more conventional with what we usually think of as correlations. Did I miss that?
That's what I said. I mean, this is a side product. Here, I mean, if you take the inverse of the asymmetric term, it's a coherence-like term.
Oh, okay, and you want to call it, okay.
Yeah, I mean,
anyway, if you're going to call it a row, that's why I got confused, because I assumed rows went between 0 to 1. Anyway, like I said, it's a nitpick.
Okay.
All right, thank you. All right. Let's move on to the last talk. It is entitled A Generic Noise Model for InSAR Time Series Based on Stepwise Error Propagation, and Sami Esfahani will be giving the talk.
Thank you, Ward. Good morning, everyone. My talk today is about noise modeling in InSAR stacks. And I want to start with FRINGE 2021 recommendations. And if you look at the document, you see one of the recommendations that communicate regarding communicating results and their uncertainties. There are two recommendations, key recommendations. One is a standardization of output products, and one is to provide error bars and easy to understand statistics with final results of the formation time series. And this talk is actually regarding both of them, mainly the second one. Why we need a noise model? Of course, it is clear, but just to review, proper quality description. Actually, we want to know how large or how wide should be the error bars. Proper weighting in geomodeling and data integration. We want to give a weight to our data, so we want to know how precise they are compared to other data and their weights in the geomodeling. Proper noise filtering. If we want to separate noise from signal, then we should know statistics and about the noise to separate it from the signal. And proper interpretation to decide what we see is a signal or it is a noise. Just very simple example that in the end of presentation I will come back to that. Here we see a time series. All the trends and linear velocity are removed already, and here we see some ups and downs in order of 5 millimeter in this time series. Is this the formation or this is noise or correlated noise actually? Or in space, I have the one simulated interferogram here, but you see in the center something around 10 or a little bit more than 10 millimeter subsiding. This is noise or this is signal. We need noise model if we want to have these kind of decisions, especially when we go to localize the formation and these localized applications. There are two aspects of quality: precision and accuracy. Precision, what is the dispersion around the mean? How wide should be the error bars? And accuracy, how close are the measurements to their true value? Regarding InSAR, the main part of accuracy is mainly because of unwrapping errors. In this talk, we're not talking about unwrapping errors and accuracy. We are mainly talking about noise models and precision. There is a poster number 83 if you want to follow about accuracy and quality of phase unwrapping. There already exists a good body of knowledge on noise components in InSAR. A lot of papers, I just mentioned a couple of them in this slide. Coherence affected noise, it means all the scattering, the correlation, thermal noise, coregistration noise, everything that affects the coherence. Atmospheric noise, coherence affected and atmospheric noise in the time series. Plenty of papers and studies. But are these models representative for final InSAR time series and products delivered by different algorithms and softwares? I think no. Why? Processing in this noise. There are different spatial or temporal filtering steps, reduce the noise magnitude, it's noise reduction we have, and different spatial and temporal filtering steps alters the noise structure, not only magnitude of the noise, but noise structure. Here, just very simple, purely white noise, uncorrelated, blue ones, with moving average, we filter that, it's smooth, but this smooth signal, it is just noise. It's already purely noise that is now, the variance of that is smaller, but now it is correlated, it's smooth. And our eyes usually try to interpret this smooth signal, smooth noise as a signal. So because of this processing in between, these currently available noise models is not representative for the final products that we have from the software. The noise structure of final time series is dependent on different factors: a scattering characteristic of the targets, atmospheric delay, heterogeneity via atmospheric noise models, data characteristics, multi-looking factor, number of acquisition, revisit time, type of the deformation that we are looking at, and the special temporal behavior of that. The kernels that we use in the space or time for filtering, they affect the final noise, and distribution location of targets that you use for this kind of filterings and interpolation. So we need some generic noise model to account for all these factors together. and in an easy-to-use way. Our rationale here to use error propagation, uncertainty propagation, we have from our already knowledge about atmospheric and scattering and all these models, the noise of the initial InSAR products, and then through processing, we want to propagate it to the noise structure of the processing InSAR results. It is complex. We have a large amount of data. There are different processing strategies between different softwares. We want to be generic as much as possible. And let's see how we want to do that. And because of the large data, the goal is finally to have one analytical closed form expression that to construct variance covariances for any set of observations that we want. Because if we want to make one variance covariance matrix for all our points in all time series, a huge matrix, we cannot use with that, but use that. But if we can make some expression that for any set of points or one time series or set of points in one interferogram, we can make then variance covariance matrix, then that's actually a goal here. So as steps, we first exploit the existing body of knowledge about InSAR noise source to propagate errors through the interferogram generation. It means from SLCs to statistics of interferograms, and then further error propagation in the filtering steps. We formulate our mathematical model is based on prediction theory, called it least square collocation, or in signal processing Wiener filtering. It is generic. It can cover different existing methodologies. It's flexible. It can digest different kind of assumptions and kernels and different noise components in it. I think it is simple. It is linear, so we can use linear error propagation for final quality. Generic functional, the mathematical model that we have, we put here Y vector is not necessarily time series. It can be time series. It can be set of points in different interferograms. It can be a spatiotemporal data set. In generic form, Rx is our functional model. Any trend or anything that we estimate from data like velocity or spatial trends. S, unmodeled deformation, something that we cannot model, but maybe we can model it stochastically. Atmospheric signal, and all other noise components, coherence-based noise components. And the final covariance matrix of this vector Y, it is the summation of variance covariance matrix of unmodeled deformation S, atmospheric A, and Qn, that is the noise components. Then in the filtering step, we want to compute something else. We want to use this Y, compute something else. That something else, I call it Z here. So Z is something that we want to derive. So the Z also decomposed in two parts. One deterministic part, that is RZX, it's our functional model, trend, velocity, whatever. And SZ is unmodeled deformation. We want finally the deformation time series or deformation product. So all deformation is there. Okay, if this is the construction of the model, then in two steps we can solve it. First, we can use solve for X using least squares. I put it in the most generic form. The weight matrix can be whatever user decides. So it is not one particular kind of least squares. Generic form of least squares, we estimate X. And then step two, we can predict actually Z. And if we combine these two equations, finally, we see that the Z that we derive, it is a one linear relationship of Y. I don't want to go to details here, but I want you to get the concept that if we can formulate everything as a linear relationship of each other, then we can easily do error propagation later. So if we have this matrix F, then we can simply propagate variance covariance matrix of Y to QZ. But how to get QY? The existing body of knowledge that I already told about atmospheric, about the scattering noise, about the deformation patterns that we have in the area. This is the big question, how to get it. I will come back to that later. But if we have this, now the question is how to propagate this in the processing chain. Challenges of full propagation is that we have some steps in time domain, some filtering in the time series. Then we have some filtering in the space domain. So somehow we should connect these two in the error propagation if we want to to apply error propagation, merging these temporal and spatial models together. What we do is we first, usually this filtering in most of the algorithms are based on the two steps. One, they apply high-pass filter in time domain and over points, or some set of points. I call it set n, initial points. Then they apply some low-pass filter in the space domain to separate low-frequency signal in space, mainly atmospheric noise. Then interpolate this atmospheric noise on other points. We call it set P, and then apply correction of this set P, and finally have a filtered time series or products on set P. If you want to do it in a mathematical way, I'm going very fast. Again, the point is not going to the details of these equations. The point is to see how we convert everything in a linear form finally. So if we, in the time, for each time series, we have this model, then based on the model that already told, we can estimate X, and then we can estimate high frequency signals that compose noise and atmosphere. And then we can write everything again in a linear form based on our initial observation yi, the equation bottom of the slide. This is just for one time series. If we have m number of points in this initial set n, then we can put all these vectors in one vector, and this operation become like this. There are big matrices, but it's possible to handle with that. And again, this final high frequency components En in the bottom, it is a linear relationship, a linear function of the observation that we have in the star. Then we go in the space domain. Then in the space domain, these vectors that we already get from time domain, this En, now we can pick one of them, for example, for kite, in the interprogram Ka, or some other interprogram, and then write some model in a space domain. That B here is the trend or special trend for Unisphere or whatever trend that we have in space. A-Ka and N-Ka is the components of atmosphere and noise in the Ka component. Then we can do again the same filtering approach. Here also, there are some kernels involved also in time. I forgot to say there are here the vector L is a kernel in space. Also, we have another kernel in time, Ka. Then again here, we can write in each interprogram the estimated low frequency corrections, that is mainly atmosphere, as a linear relationship to En. But this En, it is for En is for all the time series in all the interprograms. En with Ka is only for Ka interprogram. So we need somehow to connect these two. So we have a selection matrix here, SK, that we can connect the Ka components from all the time series and it put it in the one vector, become EK. So with this SK or selection matrix, then we can actually write the final correction as the linear component of the first vector that is all the time series in one vector. Now, if in two different interprograms we want to correct for this term, we should subtract the initial observations from the corrections that we get. That is the linear relation to the initial observations in the point N. Just I want to emphasize here the correction is over the pixels in the set P, and the N is the initial points that we use for interpolation. So they can be the same, but not necessarily. So the final precision of the filter phase that we get from this equation is it is the dispersion of the error in the dispersion of the remaining noise in the data. So initial noise that we have was this E components. Now we have the correction that is F multiplied by Y. So if we subtract these two from each other, it's the remaining noise in the final InSAR time series or InSAR in each InSAR points in each interprograms. And here again, you see that we can write it in a linear form from the original observations, and then simply we can write this error propagation and come up with the final equations. In these final equations, the first one, with the first one we can compute the variance of any target in any interprogram. With the second one, we can compute the covariance between any two phase values in the time and space domain. Two phases in time, two phases in space. In one phase in one interprogram with another phase of another point in another interprogram. All the correlations are there. So with these two equations, actually we can reconstruct whatever we want for the final noise components. And these F matrices here captures all the filtering settings, types of the kernels, location of the points, functional models that we use. And this Q matrices captures all the initial noise structures and effects of pre-processing. For example, how phase linking convert coherence matrices to covariance matrix of the final stack. So everything is there, multi-looking is there, functional models are there. So all components that we have are either in this F or Q matrices, you can find them. Just to check the validity of the final equations, we simulate very simple scenario. We simulate also different noise components, and we use our proposed analytical closed form equation to find out the covariance matrix. So I call it A here. Also, we have empirical covariance matrix by producing 1,000 realization of the noise and do the same processing all 1,000 realizations and get the empirical covariance matrix. And when we look at these two, final covariance matrices are very similar, and actually it validated the equation, at least the propagation is correct. In this simulation also, it is nice this is a very good tool to that show us what is the effect of different processing steps or different settings that we have in the final solutions that we get. Here there are 4 points, and in the 4 time series, in the right also you get the covariance matrix of 4 time series. And there are 2 covariance matrices, before filtering, after filtering. You see that before filtering we have higher variances, but with filtering we get lower covariances, but we introduce a lot of correlation in the data. So we actually convert uncorrelated noise to correlated noise. The density of the points in the initial network that we use for the interpolation of the atmosphere, filtering the atmosphere. You see, for example, for 3 points that I show with red here, the covariance matrix of the 3 times time series, it's in the below. So, and in the right, for example, you see one of the points has a very, actually the filtering doesn't affect that much a lot because there is no point around it. The revisit time, I go a little bit fast because of time. On-model deformation, very interesting. It is, we have modeled 2 different stochastic or on-model deformation, and then we see when this on-model deformation, the characteristic of that in the space is very similar to atmosphere, the filtering is not very effective, and it show up in the covariance matrices. The different kernels that we use, different kind of covariance matrix. Again, you see in the variance is not much different in the bottom row. But if you look at the covariance matrix, you see there are a lot of different correlation. It is same data set, same processing, but different kernels just used for processing. One demonstration of real data, I'm going to Tehran. It's south of Tehran, large deforming area, maximum 28 centimeter per year. I'm focusing on a small area here. I want to show you how the variance covariance matrix looks like for this data. You see this is every 6-month data, but for this data, we can create now the full covariance matrix based on this error propagation and get the error bars or standard deviation of the cumulative deformations that we have. Or we can, for different time series, again here we see the filtering, before filtering and after filtering, how much we introduce correlation, noise correlation in data. And also we can further propagate it to velocity. So we have velocity, also we have an standard deviation error bars for velocities. Come back to my first questions. This is signal to noise. We need error bars here. Error bars come from the diagonal elements of the covariance matrix that we use. Still, if we look at this 95% confidence interval, we say, okay, these ups and downs could be signal. But if we look at the covariance matrix, not, because the covariance matrix show we have correlated noise. We can simply do the test, and the test is rejected. It means it's not really the signal, these ups and downs that we have in the final time series. It is smooth, but it's not signal. It is just noise. In a space, I get the profile of this. If you look at the profile, we have a subsidence. If you put the error bars, still the subsidence makes sense that it's subsiding. But if we test based on the covariance matrix, then we see that the test is failed, and it means this profile that I show you here, it is just purely noise, but smooth noise. So this is, I conclude here, and I just focus on the last conclusion here, that based on this, I think error bars are not enough. We need somehow to address the covariance in the final data. Thank you very much.
Thank you, Sami. So let's have one question before we move on to the discussion part.
If you think of one, we'll do it in the general discussion, unless, was there a hand up? I didn't see.
Well, maybe I'll have a single question,
Okay.
a small question, Sami. So I guess it always depends on what you want to do with the data, right? So how you parameterize your problem. So the variance-covariance matrix you want to end up with in the end is dependent on whether you want to have a kind of functional description of a subsidence bowl or some kind of accelerated deformation or so. So how generic is your method for these different types of parameterization?
I think that the covariance matrix of the non-model deformation that we put there, it allows us to whatever kind of a signal we want to include in data. If we assume that the model is correct and there is not that much on-model deformation, based on this assumption, we can put this QS to 0 and apply this error propagation. Of course, it depends on your assumptions, but for any kind of quality description, we should start from some assumptions. But again, as you said, it depends what we want to do, but this is generic to digest whatever you want to do as a kernels or covariance matrix in it.
Okay, so we're now to the point of our round table, which is the more general discussion, and we are also including points brought up in the first half of this session, which was in this room yesterday morning. So could we ask Pao, and who was the other chair yesterday? Is he here? Oh, could you both come down as well, because that was in your session. And we have a few questions that are here as guides. And so yesterday's talks were actually, there was quite a common theme in terms of the closure phase and presence of phase bias and such. So that is something that is clearly being thought of by a number of people, and so there may be some good discussion points people want to continue to bring up about that. Today's session had more of a variety of different talks, but if there's a question that's lingering someone would like to bring up, then that is perfectly fine.
Yeah.
Let's
maybe just to add on to that, so we have 20 minutes here. I think what is probably most interesting is to go towards recommendations for InSAR, right? So because the scientific discussions will go on and on. So that's one remark I would like to make. So try to see what is practically relevant. And the other thing is, so which is now the questions which are projected now. It can be a lead for discussion, but feel free to come up with any other point you want to bring up. We don't want to go sequentially through these questions anyway, right? So if you want to address something, then it's fine. Frans.
So I believe that the closure phase issue is one that faces the entire community. Right now, there are lots of studies that all have their own sites. It might be useful for InSAR to establish a set of closure phase super sites, field sites where the relevant field measurements are taken, one that's maybe more arid, one that's, a variety of different environments and everybody could use that same site so that methods can be cross-compared and results can be cross-compared. We have all the relevant reference data we need.
Now you're then also referring to having ground truth at these super sites, because I guess doing it, probably people will come up with the same results, but the thing is what is going on. Huh? So collaboration maybe with other parties which could provide soil moisture or whatever.
Another comment or suggestion? Yes.
Yeah.
I'm wondering, I'm addressing the first
Can you speak in the
question.
microphone, please? Just
Okay. I'm addressing the first question, and I'm wondering that all the approaches presented here process a full graph or a large set of interferograms, and usually they don't address their coherence because for many of the interferograms it's just pure noise.
I didn't get the point, sorry.
I wonder why most of the algorithms which were presented use all the stack, while most of it may be just noise because of the low coherence, and coherence is always non-zero, even for pure noise.
Yeah.
Yeah, so if I can reinterpret that, maybe I didn't understand it correctly, but how can we be sure that we are estimating a non-zero closure phase rather than something that's an artifact of the noise in the measurement? Is that the question? So that's a good question. Anybody? Dave, you want to make a, or you?
Just back to the closure phase and the Cal-Val aspect of this. GNSS measurements can also measure soil moisture with reflections from the surface, people do. And so those are obvious sites to do Cal-Val, closure phase, InSAR, GPS all together. And so, but that's at L-band. And I think at C-band, the closure phase is going to be very different. So we have some natural L-band closure phase Cal-Val sites to use.
Elizabeth? Oh. Well,
I mean, continuing with the same
hand was up
comment,
first.
there is a companion system from Roselle, is Simmer, which is a microwave, passive microwave. So one of the, and SMOS and all these people there, one of the main variables they are targeting is soil moisture. So maybe they have already these super test sites with soil moisture measurements. It's true that this Simmer is working at different frequencies, but at least they may have ground truth measurements of soil moisture. You could combine in the frame of Roselle, Sentinel-1 NG and all this. So you don't need to make new things. You can maybe collaborate with those people to get these test sites to get the information about the phase closure.
In terms of Cal-Val, I think that we do have a lot of soil moisture ground truth, and what we have less of is ground truth about how vegetation moisture is changing. We have proxies like NDVI, but not so much not very many in situ measurements of vegetation change, and especially vegetation moisture change. So if we're looking to more sensors, that's what I personally would find the most useful in terms of isolating different sources of closure phase.
Charles?
Microphone, please.
Is there a consensus that you can actually separate out the closure phase from, let's say, deformation? Can you separate those two terms? Methodologies for doing that, and then the closure phase itself does become an interesting signal for whatever application.
So let me try to, since we're trying to eventually figure out some kind of recommendations for ESA, let me just float sort of a general idea and then we can comment. I mean, this is clearly a topic where there are multiple people working on it now. And so it seems to me that it would behoove us to, at a future meeting that many of us will attend, at least have a session or two dedicated to phase closure papers And if this is really an open issue and there's a lot of things that are not well understood and requires a larger number of people, folding in different kinds of ground truth and that kind of thing, is this something we might want to think of in terms of having an informal working group or even a focused meeting at some point in the surface, in the future? So the idea is that if there are, if there are 25 people who are all working on this, that's a lot of people to work on exactly one thing, and so there may be something to gain from that. So we could perhaps list a variety of things that we might want to propose under the auspices of FRINGE or of ESA or of NASA or the International Consortium or whatever.
Yeah. Irina.
I think diversity in the research is fine, Howard, like everything else. 25 people working on it, I think it's okay.
Oh, no, of course it is. I mean, I'm always of the let 1,000 flowers bloom approach, so I'd rather everybody would look at it.
Okay, yeah, thanks. So I think it's also important to understand or to develop algorithm really to see how vegetation is really impacting this closure phase. Not only, there's three components for me. The one is a deformation, the other thing is a soil moisture, and the third thing is the vegetation impact, which we see is quite strong. And the question is, can we first decouple the effects of soil moisture and vegetation on deformation? And then the second question is, can we decouple soil moisture from vegetation in order to get soil moisture really, and not the vegetation content? So there's a lot of questions that we have, and I think we need to develop more understanding on it, but also algorithms. So for me, it would be very important to have a study actually, not only to discuss, but to have a kind of study which is really framing this, and that people can work on this study, somehow supportly financed on it.
This one way up here and then back to you.
Hello. I agree with the idea of the supersites. I think it's a very good idea. And maybe it would be interesting to have several bonds, C, X, and L, and maybe X also. Because yesterday there was a comparison between C and L. It was very interesting.
Yeah, thank you. So let's go to Carlos and then...
Just in connection with question number 4 and the use of polarimetry, if I got well, you want to separate the different components, deformation, vegetation, and soil moisture. That's right. So maybe polarimetry could be used to, not to make something operational, but to separate the components. Because there are already some research directions in the polarimetric community trying to separate vegetation from soil moisture. So maybe this could be used. The question mark is that if we are going to have a data set, a polarimetric, interferometric data set at the given frequency, C-band, L-band, I don't care, but the problem is to have the data together with the soil moisture. And that comes back to the first question about tessite with ground truth. So theoretically, it would be possible to have that study, but only if we have the data, the proper data, that could be done with a ground-based sensor, for instance. You don't need to go to space, and also the ground truth. Theoretically, it's possible, but to have all the ingredients on the same time in the same place is the difficult part.
The question is to use airborne, or the comment is to use airborne sensors as well. There are a couple of questions way up over here. It's easy to neglect people because it's too many steps for the microphone.
So in terms of the phase closure mitigation strategies, there are already actually some methods already developed in the literature. Some methods by Yuji that described yesterday, and also another method by Falabella in Italy that developed a mitigation strategy for the phase bias, and also another method that we developed in Leeds. So one of the challenges here is the main assumption that most of these methods that I use is the availability of a long-term interferogram which is bias-free, the phase bias-free. And so this assumption in many cases is under question because in the decorrelated region, there are many pixels for which we cannot have this long coherence. And so this assumption might not be true for many pixels especially in the highly vegetated region. So maybe the main challenge that we have to solve a robust solution is to find a strategy which is not dependent to the availability of the long-term interferogram to mitigate this issue. And also it is very important to check the universality of the method. I mean, most of the methods have been checked in several studies, but it is good to check the universality of this method in several different scenarios with different scattering mechanisms.
Thank you. And I think there was another question, just two down.
Yeah, so I'm talking about the first questions. So we all know that phase closure are caused by the multi-looking operation because it's use both the phase and amplitude to do the multi-looking. That's why it breaks the phase consistency. So I'm wondering if there any way we can look back to the multi-looking. So the way how we do the multi-looking, there any develop some algorithm approaches, try to use different alternative ways to migrate or remove the phase closure from the very beginning. That's my suggestions.
Okay, yes, thank you. Over here.
So, different topic. Moving on to Sammy's talk at the end there. One of the recommendations from the previous Fringe was that we need to be implementing uncertainties and understanding the covariances in the data better. And Sammy's talk is a great progress on that. But we don't see that being in use in the majority of papers publishing time series yet. I think there's significant work to be done there still to actually take what Sammy's done or others and implement that fully.
Yeah, don't feel like you have
Yes,
to comment only on phase closure.
Oh, okay, so
maybe can I just bring in a little bit different topic?
Well, I think Andy had a question.
All right,
There's a question up here as well.
Okay, go ahead. Yeah.
So I saw this session C questions is all 4 questions about the keywords, the non-closure phase. So, and then I try to characterize a little bit. So the first question is about statistical methods, how to avoid that one. And the other question is about how to explore the physics information signal inside that one. So I first just focus on the first question is, should a study in this direction to remove the non-closure phase is initiative? I think it's yes, I totally agree because I totally recommend that there should be a dedicated study to understand this one because application in information is important and critical for everyone. Especially true when we go to filter mission which related to the longer wavelength like the Rosa L or the NISA. With the longer wavelength, we better penetrate to vegetation. In this case, we can understand what happened under beneath of the forest. And also related to 3 other questions, we using that non-closure phase to retrieve the signal under the forest, like something like vegetation, moisture, water content inside the forest, or even maybe we could use something like non-closure phase to understand some physics like forest high, forest biomass. I mean, there will be a possibility to explore that signal. So about the second question, so what kind of study to initiate to achieve this one? I think that's we can start with airborne data because with airborne data we have a lot of airborne data from the L band, even with the B band. And spatial we have a lot, but a little bit limited to everyone. But the airborne, the InSAR, they open a lot in the data for the L band data. So it's free for everyone under the scientific research. So about the third question is, do we need something like evaluate the performance inversion under different conditions with respect to vegetation cover? I think it's true because under the forest everything is crazy. So basically, that in the forest we had to make some assumption like, okay, is there any failing? Is there any phase center to be sure that the non-closure phase is okay or not? So we need to understand a lot under the forest with respect to the soil, to the basalt. Basalt is more straightforward. And the last question is about polarimetry.
Since you were making many, many comments, I would like to give Andy a chance to talk, and
So,
then
I'll
Ramon
let
a chance to change the subject.
okay, sorry.
We don't comment more about them. There are more.
I'm sorry. But everybody needs to talk.
Yeah, just one comment. I think that's maybe partly the point that was just made, but I think the idea of a test site is a great idea. It's important then, I think, to have multiple sensors with different wavelengths. So if we do airborne, that's great. We can do all kinds of different things. But yeah, we see clearly that different wavelengths will help, I think, distinguish between soil moisture and vegetation characteristics.
So before we switch to the other topic, I want to make two observations. One is that I hope that people are listening to this and we get a plethora of proposals to investigate all of these things, and people are getting good ideas and starting to think about it. And I forgot what my second point is already. Oh yeah, no, we've already made a great deal of progress at this meeting, because yesterday everybody was calling phase closure phase bias, and now we're saying phase closure, so we're recognizing it as a signal with information in it, to parrot what Ricardo was saying yesterday. So we've done something at this meeting. All right.
Yeah, just on a whole different topic, maybe something to discuss further in the coffee break. So in the previous time when we gave recommendations to InSAR, it was many times because there were new missions coming up. Now the next two missions will be Sentinel-1C and 1D, which are operational. We cannot influence that much. But then we're going to have the Sentinel-1 next generation and ROSE-L together. And I think the current line of thinking is that so both missions with 2 satellites, 6-day repeat, if you have both of them, to intersperse them symmetrically. So that means that you get one acquisition with Sentinel-1 next generation in C-band, and then 3 days later you get from the same point in space, from the same orbit, with the same, more or less the same resolution, the same viewing geometry in L-band. So we have, let's say, equidistantly spaced sampling. 1 day C-band, 3 days later L-band, then C-band again, and so forth. And I think at this time, it is because people are thinking about these concepts, it's also good to help them and to come up with different arguments. I think it's a great scheme, but I think it's something that is worthwhile for us to consider and maybe come up with different ideas for InSAR to consider.
I remember also about the validation. I know our colleagues in CONAE with SAOCOM, they are routinely producing soil moisture measurements in Argentina. And there is the PUMAS program between ESA and CONAE. So maybe that could be an avenue to explore, to combine SAOCOM with Sentinel in Argentina. I think Sentinel in Argentina is only 12 days, but I mean, there are some technicalities that you can solve. But at least there is already a framework of collaboration between InSAR and CONAE, and maybe the Argentinians are producing soil moisture, so that could be a good setup to
for the
produce
alternating C-band, L-band.
Yeah, I mean, to explore if you can have the data, the ground truth, the estimations to test these kind of things of phase closure, even on national scale.
Yeah, and just to add on to that, don't forget that InSAR, which launches in a short few months, has got 2 frequencies, it's got a large soil moisture group, and there will be many, many field sites and things like that with open data that will be available to everybody. So just add that into your list.
So Ramon, building on what you said about, and following from your talk, Howard, how the automation of the data products now and the release of data products, particularly in this now geocoded SLC, which we're trying to encourage, I think. But I think, is it on us to set some minimum requirements on the DEM qualities people are using and how regularly they are updated when they are delivering these geocoded SLCs as standard data products?
Yeah, I mean, if this is an issue, then we never definitely want to say that. And, you know, I mean, the Copernicus DEM is great, but it would be nice to have 5-meter postings at 0.5 meter resolution. I mean, would that make things better? If so, can we think about, you know, tandem X or L or whatever it is in the future to do it again and do it better? I mean, that we want to keep improving.
I have one more can of worms, and I admit that I'm both frequency and geographically biased here. When we talk about signals that I don't think we understand enough, with L-band coming up with Roselle and InSAR, we'll have suddenly coherence 365 days a year in many places. And we'll run into having to better understand the impact of snow. I don't think we know enough yet how snow impacts the phase and how it may impact closure phase if there's gradients of moisture in the snow. And I think more study on, first of all, how to utilize the signal to understand snow, but also then add it to the list of phase components that we have to separate in a time series analysis, I think is also something to look into.
I want to point out some minor mathematical point. All these processes that involve closure phase are something like rain when coherence breaks down, or there is, regarding vegetation, there's maybe some harvest where coherence breaks down, but in the interpretation, the time series are put together as if they were continuous, while in truth we do not know how it goes on. And this missed a discussion of that in the talk, so that's why I wanted to point this out.
I think probably we should slowly start to wrap up if people still want coffee.
Yeah, so if somebody wants to raise a new topic, do that. Excuse me, we will talk at the coffee break about it, but let's get it out. So you get the last
maybe
word.
one remark there on Ramon's line on spacing the. Yeah, it's me. So on Ramon's line on spacing the satellites there, I want to bring up the topic a bit of error handling. I mean, you can either prioritize the temporal sampling by spacing them equally apart, but having L-band, C-band, and maybe others right next to each other, then really observing same atmospheric problems. This may be value more in terms of error handling than having a temporal sampling. So people maybe have to think about it and make up their mind which value more.
All right, thank you. And with that, we will wrap. So thank you to all of our speakers and to all of you who sat in the room, and we'll all talk at the coffee break. Well, I know you just had to stand there, but...